want to welcome you to the class today. In the class of today, we are looking at something very important, and that is rate of chemical reaction. Meanwhile, I want to say Happy New Year to all of us and wishing us prosperous year in Jesus' name. I want you to know that I have done a mathematical analysis and the chemical analysis of this year, and I've also discovered that there's no need for anaerobic respiration. This year is going to be a year of rest for you, for your family, for everyone in Jesus' name. Because in my research work, I discovered that all the holidays that we have this year fall into weekend. After the class for now, I want you to check it. You will see January 1 is weekend. You will see that April 15 is weekend. April 18 is weekend, in such a way that each of the holidays that we have this year either increase the holiday by increasing to Friday or to Monday, increasing the time of rest that we have every weekend. And that is why this holiday is very, very important. So this year is going to be a year of rest for all of us in Jesus' name. And let me quickly take us through rate of chemical reaction. You see, rate of chemical reaction is also known as the speed at which chemical reaction takes place. Rate of chemical reaction is also known as the speed at which chemical reaction also take place. Now, the rate of chemical reaction can be defined in three ways. Number one, it can be defined in terms of the rate at which mass disappear, or in terms of the rate at which the product is formed, or in terms of the conversion rate. If we have, for example, elements 1 and 2, R1 and R2 being our reactants, and that reacts together to form our products, then we can look at rate of chemical reaction among the reactants as we look at the mass of the reactant that disappear. In the product form also, we can also see the mass of the product that is formed. We can also look at the conversion rate, how the reactant is being converted to the product. These are the three ways by which we can define rate of chemical reaction. Now, if we pick them one by one, we say that the rate of chemical reaction is the number of moles of reactant that is used during a chemical reaction. The number of moles of reactant that is used during chemical reaction. In that way, if the masses of a substance is 20 and we start the reaction, you see that the mass will be reducing to 18, 16, 14, 12 and so on. If we calculate the mass that is used up, that will be on the increase side. It will start from 0 into 2 into 4 into 6, 8, and it will continue. So if we use the above data to plot graph, we are going to have two types of graph. If we use the mass, that is 20, 18, 16, 14, 12 to plot the graph, and we use the mass that is used up, that is 0, 2, 4, 6, 8. I know what I'm saying now. If you use the mass that is left or the mass that is used up, we are going to have two types of graph. So here, if you plot the graph, we are going to have two types of graph. The first one will look like this, then the second one will look like this. Let me pick then one after the other. Deal with the first one. You see the mass that is used up. So you see that mass will be increasing gradually. See, the mass will be increasing gradually. The mass will be increasing gradually. The mass will be increasing gradually. When it gets to this point, the rate of increase will reduce. And we get to this point now, you see at this point, you see there will be end points. The rate will not go up again. So this place is known as the end point. Now the mass that is used up is increasing gradually. So we can define the rate of chemical reaction in terms of the mass that is used up. Now what about the mass that is left? Initially we used 20 gram. 2 gram was used up, so it reduces to 18. Another 2 gram was used up, it reduces to 16. Another 2 gram was used up, it reduces to 14. So the mass that is left is reducing from time to time. In this case, you can see that the graph is reducing. It is reducing sharply, 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 until you get to a point. As you get to a point that it is no longer reducing, and at that point is known as what? As the end point. That means we have two types of graph. We have the reducing graph and the increasing graph. So we can also define rate of chemical reaction in terms of the product that is formed. We will say that rate of chemical reaction is the number of moles of products formed in the chemical reaction per unit time. The amount of the product that is formed per unit time. So we also can express that in the graph, and that graph also will give us the two types of graph that we have said the other time. And then we can also define rate of chemical reaction based on the reaction, in terms of the reaction is parts, or how it is produced. If that is the case, we say that rate of chemical reaction is the mole of the reactant used for production to produce a mole of product per unit time. In whichever way it is said, rate of chemical reaction is the speed at which chemical reaction occurs. Rate of chemical reaction is the speed at which chemical reaction occurs. Now, if we have an experiment and we take 20 gram of calcium trisulcarbonate 4 in 3 places, we leave one, it is a lump that is big like stone. We have one that is broken into, and we pour each into conical flask containing 0.5 mole per dm cube of hydrochloric acid, and we know the efficiency in each case. You will see that there is a glass A, glass B, glass C. Each of them contain hydrochloric acid. Then you pour those ones that look like lump. You pour it there. Those ones that look like pellets broken into pieces, you pour it there. Those ones that grind into powder, you pour it there. Which one do you think will give more effervescence? Which one do you think will give more gas? Which one do you think that the rate of chemical reaction will be very fast? A will be slow. The slowest is A is slow. That's the slowest. C is very fast, the fastest, and B is intermediate. If we calculate the rates and sketch the rate at which the masses are used up per unit time in each of the case, then we are going to have what is known as the rate curve. So A is slow, and that was the slowest. C is very fast, and that was the fastest, and B is in between it. So if you look at the time for 3 minutes, 6 minutes, 9 minutes, 12 minutes, and 18 minutes, and you look at the mass that is left, we can easily calculate the rate of chemical reaction. We have terms used in determining the rate of chemical reaction. We have the mass of the product, we have the mass or volume of the reactant. We have terms that is used in calculating a rate of chemical reaction. We have the mass of the reactants used. We have the mass of the volume of the products that is produced. We have the color change. We have the change in pH or pressure of the gas. Each of the measurable terms can be used in determining the rate of chemical reaction in each case. Now, if we plot the graph, then we have one that is known as rate curve. Rate curve. So, rate curve is the graph that shows the rates of chemical reaction. Rate curve is the graph that shows the rate of chemical reaction. And number 2, we have endpoints. Endpoint is the point in which the reaction stops. It stops, 1, maybe because one of the reactants is used up, or because one of the conditions is altered. It can stop because of so many reasons. But one of the major reasons that stop rate of chemical reaction, that brings a reaction to endpoint, is when one of the reactants is used up. So, endpoint is a point in which the reaction stops. Rate of reaction or concentration. Rate of reaction, which is, let's denote that with K, and that is concentration of A, where K is called rate constant. 60 centimeter cube of hydrogen peroxide is decomposed according to the equation in 40 seconds. That is 2H2O2 to give us 2H2O plus oxygen gas. And that reaction takes place in 40 seconds. The cell should calculate the rates of hydrogen peroxide. We should calculate 1, the rate at which the hydrogen peroxide is decomposed, the volume of oxygen that is produced, and the rate of oxygen that is produced. Can you remember this? We are going to apply Gay-Lussac law of combining volume. When gases react, they do so in volume, which is a simple whole number ratio one to another, and to the volume of the products, provided temperature and pressure remain constant. If ratio 2 is 600 centimeter cube for hydrogen peroxide, for oxygen also ratio 2, for water also ratio 2 be 600 centimeter cube, but oxygen is just 1, therefore that one will be 300 centimeter cube. Therefore, the rate of decomposition of hydrogen peroxide will be the volume of hydrogen peroxide that is used up, which is 600, divided by 60 seconds, which is the time, and then that will give us 15. And that will give us 50 centimeter cube per seconds. 50 centimeter cube per seconds. And likewise, that the volume of oxygen that is produced, and that will be 300, and that will be 300 all over 40 seconds, and that will be 7.5 centimeter cube per seconds. I'm sure you'll be able to do that and submit that, please. I'll be waiting for the answer. Then we have collision theory. is a powerful theory that is very important in rate of chemical reaction. Collision theory states that before reaction takes place, the reactant particle must collide together. They must collide with one another and with the wall of the container. Only a fraction, that means not all, only a fraction of the collision results in chemical reaction. The one that results to chemical reaction is called effective collision. It's called effective collision. So effective collision is that part of the collision that results in chemical reaction. Is that results into chemical reaction. These colliding reactant particles must possess minimum energy. This energy is known as activation energy. The energy that must be overcome, please correct that please, before a reaction can take place is known as energy barrier. If energy barrier is equal to 50 joule, the activation energy must be equal to 50 joule as well, because it must be overcome before reaction can take place. So we can now state collision theory, and we say that collision theory therefore states that before a reaction takes place, the reacting particles must collide with one another. Please put S in particle. I take that place again. The collision theory states that before a reaction takes place, the reacting particles must collide with one another. Here we have the factors that affect the rate of chemical reaction. I'm sorry. These factors of chemical reaction, in the moment to remember, NLC, STPS, you know all the 7 of them. N stand for nature of reactant, L stand for light, C stand for concentration of liquid or solid, S stand for surface area, T stand for temperature, P stand for pressure of gas, and C stand for catalyst. NLC, STPC. So, can you try it? Now let us see how each of these factors actually affect the rate of chemical reaction. The nature of reactants. There's a series called activity series. The way and the rate at which chemical reacts varies from substance to substance. Depending on this series, for example, if sodium, zinc, and gold react with hydrochloric acid, that of sodium will be super fast. That of zinc will proceed normally, moderately, while that of gold will not react at all. Why? Because sodium is very high in the chemical series, zinc is at the middle, whereas gold is at the bottom of the activity series. Therefore, hydrogen cannot displace sodium. Sodium will rather display hydrogen, therefore it will react very fast. That of zinc will be moderate, but that of gold it is not possible because hydrogen is higher than gold in the chemical series, in the activity series. Therefore, gold can. In this nature of reactants, and that is the activity series predicts a lot of things. The activity series makes us understand that potassium, sodium, calcium, magnesium, aluminium, they are extracted through electrolysis, and zinc, iron, tin, and lead are extracted by burning with carbon, whereas copper and mercury are extracted by burning with air, whereas silver and gold do not need to be extracted at all. We have other factors of, apart from the nature of the reactant, we have other factors like light, like concentration of liquid or solid, temperature, pressure, and surface area. Each of them, you remember, if you count, this is going to give us 5, and we have 7. I've mentioned 1 before. This is the remaining 5. It means 1, which is catalyst. I've not discussed. Here, I just want to say that all of them increase the rate of chemical reaction by increasing the rate of collision. Light, concentration, temperature, pressure, surface area. They increase the rate of chemical reaction by increasing the rate of the collision of the reacting particle. But for catalyst, that is not the same. In the other way, what catalyst does is that catalyst reduces the activation energy so that the rate of chemical reaction can be increased. Therefore, catalyst increase rate of reaction by reducing the activation energy. If we have the rate of the graph like this, and we have the activation complex, and we have activation energy, and we have the uncatalyzed reaction, we have, then catalyst will reduce it, we have reduction activation energy, then we have the catalyzed reaction will reduce there. So catalyst increases rate of chemical reaction by reducing the activation energy. So more reactants can attain the activation energy because it is reduced, and the reaction can produce very fast. Now I want to put a tutorial question here that I would like you to answer, and please send to me and let me see how it occurs. I said mention examples of photocatalyzed reaction, a reaction that is increased by light. Easily you will remember photosynthesis. Yes, it is induced by light. Then number 2, we have reaction of zinc rod with 0.1 mole per dm cube of hydrochloric acid. He has to mention ways to increase the rate of chemical reaction. Since it is zinc rod, we can grind it into powder. That will increase the what? That will increase the surface area. Very good. We can increase the concentration of hydrochloric acid as well. Then since it is liquid and solid, there's no need for pressure here, so we can work on the rest. Then number 3, in the reaction of hydrogen with nitrogen, then the reaction is there. Mention how to increase the rate of chemical reaction. These are gases. Hydrogen is gas, nitrogen is gas, and the gas is being produced. So we can now just look at, okay, pressure will be there, which is very important, and since it's not a photocatalyzed reaction, then there's no need for us to look in the direction of light. Then guess the answer now, and please send to me as soon as possible. Thank you, good night, and God bless.